Uh, all right, so welcome everyone to this HEP-TN Seminar. Hope you're all doing well and managing the Corona blues. It's a great pleasure today to have Philippe Corboz from the University of Amsterdam, um, who will be giving us an overview of the projected entangled pair states and also discuss some recent developments in this direction. So Philip, thanks a lot for giving the seminar, and please take it away.
Okay, thank you very much, Suki. Let me also thank the other organizers for giving me the opportunity to give a talk here in this virtual seminar series, which I think is it's a really great initiative. So I would like to tell you about iPEPS, or infinite projected entangled pair states, which is a tensor network ansatz to represent 2D wave functions directly in the thermodynamic limit. And let me just, as a disclaimer at the beginning, let me say that my background is not high energy physics, but condensed matter physics. So besides the further development of iPEPS, our group is mostly focusing on applications of iPEPS to challenging problems in condensed matter physics. So I have not worked myself on the applications in high energy physics, but of course, the whole approach is very promising as well for these type of applications, as for example, lattice gauge theories. Okay, so in this talk, I'm not really going to focus on applications, but I thought what could be useful for this community is to give you a more broader general introduction to the iPEPS approach. So I will tell you about the iPEPS ansatz and also the standard involved algorithms for ground states, so for the contraction of the tensor network and also for the optimization. So this is going to be the main part of my talk, giving you this overview. And then in the second part, I will build up upon this and tell you about more recent developments on the method side, so with iPEPS, including finite temperature simulations with iPEPS, and then computation of excitations with iPEPS. And then very briefly, I will also mention what's called finite correlation and scaling, which is an approach to study continuous phase transitions. Okay, so that's the plan for today. Let me now just very briefly start with a general motivation, which in the end was also my personal motivation why I started to work on tensor networks more than 10 years ago. Namely, you would like to understand the emergent phenomena in strongly correlated quantum many-body systems. Of course, there's many different examples that one can mention here. And let's say the topics that we are mostly interested in our group are the systems, so models related to high TC superconductivity, quantum magnets, frustrated systems, and then also new phases of matter that you could realize in ultra-cold atom systems. Now, the study of these problems is in general very challenging because typically these models don't have an exact analytical solution, and then typically standard approaches like mean field or perturbation theory typically fails here. And that's why often accurate and efficient numerical simulations are really essential here to get insights into these systems. Now, one of the most powerful methods to study quantum many-body systems is quantum Monte Carlo, which is based on the idea to sample this exponentially large Hilbert space or configuration space statistically, and which comes with a computational cost which only scales polynomially in system size and not exponentially. So it's really a very powerful approach for many spin and bosonic systems. So take, for example, the 2D Heisenberg model, which has a ground state which has antiferromagnetic order. And if you take this state-of-the-art study by Sandvik and Everts, they consider the system sizes up to 256 squared, which corresponds to really a huge Hilbert space. But with quantum Monte Carlo, you can deal with this and then study quantities like here, the sublattice magnetization up to a very high accuracy. Okay, so it's really amazing what you can do with quantum Monte Carlo if it works. However, there's this big but here, namely that it fails for important classes of models. So it fails in general for fermionic systems and also systems which are frustrated due to this infamous negative sign problem. Okay, so I will not go into the details here about what the negative sign problem implies in the end, is that the computation time scales exponentially with system size and inverse temperature, such that you can't really access large systems at low temperatures if the quantum Monte Carlo suffers from the negative sign problem. Okay, so in order to make progress in understanding strongly correlated systems, it's really essential then to develop alternatives to quantum Monte Carlo which do not suffer from the negative sign problem. And in the past decades, there has been a lot of progress with a variety of different approaches. So that's an incomplete list here. And in the end, all these methods have their own advantages and disadvantages. So there's no magic black box method which can solve everything. But in the end, one can really say that there has been a lot of progress with various approaches. And among the most powerful approaches are tensor network algorithms. And these, as you surely know, have already been extremely successful for the study of one-dimensional systems, which is mostly thanks to the well-known DMRG method, right, which has the underlying matrix product state as a tensor network ansatz. So I can really say that DMRG has revolutionized the study of one-dimensional systems in the past decades. But there exist also other types of tensor networks that you might know, like the MIRA, the multi-scale entanglement renormalization ansatz, which is a powerful ansatz for critical systems in one dimension. And there exist also the generalizations of this idea to higher dimensions, like a PEPS or a 2D MIRA. And of course, the goal here is to repeat this enormous success of DMRG in higher dimensions with a tensor network that is specially designed for 2D systems. But now the problem is that the involved algorithms here are substantially more challenging than in one dimension. And that's in the end the reason why it actually took several years to come up with practical algorithms and make this really a practical tool in practice. However, in recent years, there's really been a lot of progress, and especially PEPS and iPEPS have become very powerful tools which are now applied to many systems successfully by several groups. Okay, so I will mostly focus here in this talk about on PEPS and iPEPS. Okay, so let me start with an introduction to the iPEPS ansatz. And for this, let me just very briefly remind you of the main idea of a tensor network ansatz. So I guess most of you know this already, but for completeness, let me mention it here. So the main idea of a tensor network ansatz is to have an efficient representation of quantum many-body states, and typically the ground state of some local Hamiltonian. So let's make an example with a lattice with 6 sides, where each side is described as some local Hilbert space, for example, with dimension 2, if you take a spin 1/2 system. So in total, we have here 2 to the power of 6 basis states, or to represent the state, we need in general 2 to the power of 6 expansion coefficients, right? So these are the expansion coefficients of the wave function in this tensor product basis, where each ik goes over the 2 basis states. Now we can represent this multi-dimensional array or tensor also with this shape here with the 6 legs, which correspond to these 6 indices. And the idea is now that we decompose this big tensor into small pieces, so into a smaller collection of smaller tensors connected by lines. And that's in the end a tensor network. And the structure you see here, that's a matrix product state, right? But of course, there's many different ways how we can decompose this big tensor into a smaller network. Now we can evaluate the network simply by multiplying the small tensors together and sum over these joint indices, A, B, C, D, and D. And if we do this, we obtain a new tensor psi tilde, and the goal is now that this is an accurate approximation of our exact psi. And the big difference is now that here we have a number of coefficients which grows exponentially with system size, whereas in a tensor network ansatz, it only scales polynomially with this bond dimension D here, so the dimension of this index and the number of lattice sides, right? So that's what we then mean by an efficient representation of a quantum many-body state. And the reason why such a decomposition is possible is because the states we're interested in are special. So if this is our entire Hilbert space, then the states that we're interested in, so the ground states of local Hamiltonian, only occupy a tiny region in this big Hilbert space. And what makes them special is that they typically obey the area law of the entanglement entropy, which means that the entanglement entropy of some region A here scales not with the volume of A, but only with the size of the boundary of A between A and the rest of the system. Okay, so tensor network is not necessarily a good ansatz for any state in the Hilbert space, but it's designed in such a way that it can reproduce a certain entanglement scaling, like such an area law here. Okay, so let's go back to our matrix product state here, so which is an ansatz in one dimension. So again, we have exactly one tensor per lattice side, and they're connected by some horizontal bond with a bond dimension d here. Now one can easily see that this ansatz reproduces an area law in one dimension, right? So if you imagine, if you bipartition your system here in the middle, and then look at the entanglement entropy that you can reproduce as a function of block size L, we can easily see that the entanglement entropy, so the rank of the reduced density matrix, is going to be bounded by the bond dimension d here, so by the number of states we keep, such that the maximal entanglement entropy that we can obtain is bounded by log d, log the bond dimension, which is a constant independent of the system size, which corresponds to an area law in one dimension. Now, early on, people wanted to use this idea also to simulate systems in two dimensions. And the simplest thing you can do is to simply put a matrix product state on a two-dimensional lattice with such a snake here, right? So in the end, this boils down in mapping your two-dimensional system onto a 1D system with long-range interactions. Now one can do this, but now the problem is if you look at the entanglement between left and the right side, if we make a cut here, is that the area law in 2D implies that the entanglement entropy will grow linearly with the cut length here, which then means that the bond dimension between the left and the right side has to grow exponentially with the cut length L here, right? In the end, it makes intuitively sense. As we increase the system size, the entanglement will grow, and all the entanglement will be carried by this single bond here, so it will need to grow exponentially with the size L here. So it's exponential only in the linear system size and not with L squared. So it's still better than exact diagonalization, let's say. Now, this does not mean that you can't do this approach. And actually, there's many groups who successfully apply this approach to study systems in two dimensions. And what people typically do is then do simulations on long cylinders where this length L here is not very large. And then if your cylinder is large enough to capture the 2D physics, then you're essentially done. Okay, but this approach does not scale to arbitrarily large system sizes in 2D. And now two-dimensional tensor networks have been developed in order to overcome this exponential scaling. And the trick in the end is just to add more connections in your network. And then this naturally leads to this PEPS, or project in the entanglement pair states, which is a natural generalization of the MPS to two dimensions. So, right, we also have here one tensor per lattice side, but they're now living on a two-dimensional lattice, connected each tensor to its nearest neighbor. Now, we can easily see that this PEPS reproduces an area law in 2D in a very natural way. So imagine if we bipartition our system in the middle, then the trick is now that the number of bonds we cut here scales with the length of the cut. And each bond that we cut here can contribute at most log d to the entanglement entropy, which means that the entanglement entropy is naturally bounded by an area law, something that scales linearly with L. Okay, so a PEPS naturally reproduces an area law in two dimensions, so we can go to, this really scales to arbitrary system sizes in two dimensions. And instead of looking at finite systems, what we can also do then is to look at wave functions directly in the thermodynamic limit. So that's then called an iPEPS, or infinite projected entangled pair state. And the advantage of this is that then there's no finite size and boundary effects anymore. Now, if your state is translation invariant, you can simply parameterize it by a single tensor A here, which is repeated on your lattice. So in the end, that's really a very compact representation of an infinite 2D wave function. But since we are working in the thermodynamic limit here, translation symmetries can also be spontaneously broken. And that's why what we do in practice is to use a certain unit cell of tensors, which is repeated. So if you think about the antiferromagnetic state in the Heisenberg model we had before, with two different spin directions on the two sublattices, in this case, we would use an ansatz with two tensors A and B, one tensor for each sublattice. Or more generally, what we do is to use a certain unit cell of tensors. So here would be an example of a 4 times 2 unit cell, which is repeated on the lattice. And in the end, this unit cell has to match the structure of the ground state, so the symmetry breaking pattern of the ground state, which of course, typically we don't know in advance when we start, when you look at a new model. So what we do in practice then is to run simulations with different unit cell sizes. Each unit cell might stabilize another type of low-lying energy state. And then in the end of the day, we then have to do a systematic comparison of the variational energies to see which unit cell gives the lowest variational energy, which then corresponds to the true ground state of the system. Okay, so that's the iPEPS Ansatz. And as any other tensor network, this is just a variational ansatz, so which can represent different states depending on the variational parameters which are stored in the tensors. Okay, so the next step typically is then for a given Hamiltonian to find the optimal parameters stored in these tensors, right? So we want to have the best approximation of a ground state of a given Hamiltonian represented as a PEPS. And now the two most common approaches to do this optimization is on the one hand doing an energy minimization, so where we go down in the energy landscape to find the minimum. And another family of approaches is based on imaginary time evolution. So I will tell you about both these directions later in the talk. And then once we have found the best state, we want to compute observables from the state, right? Like correlation functions or an order parameter. And for this, we have to contract the tensor network representing this expectation value here. Now, in the case of an MPS or also the MIRA, this contraction can be done in an exact way. However, for PEPS and iPEPS, you cannot contract it exactly, but you need some approximate method to do this contraction. And this is also something we're going to discuss in more detail in the following. Okay, so these are kind of the basic ingredients of ground state algorithms for PEPS or also for any other tensor network. So at this point, let me just quickly stop and ask if there are any questions up to now. Okay, so this was a rather basic introduction, so let me continue then.
Sorry, I got a question, but yeah. So the contraction, this issue of computing observables in a not exact way also affects obviously calculating the energy, right? It's one of the observables.
Yes, that's right.
It also affects finding the ground state.
That's right, exactly. So this is also in the end part of this. So okay. in the end, so there is an approach which does not involve the computation of the expectation value, as I will show you later. But in general, yes, it's true that this, of course, feeds back in here as well. Yes, I agree.
Okay, thanks.
Okay, so then let's go a bit more into the details of this contraction here. So let's assume we would like to compute the norm of a PEPS, and here we just do an example of a 3 times 3 PEPS. So that's the ket of the wave function, and here we have the bra of the wave function. So the first thing we can do is to bring these two layers together and then multiply always the ket PEPS tensor to the bra PEPS tensor, so that we end up with this network here, where these tensors have double lines in between them, so each with bond dimension d. Or another way to represent this is to combine the two d lines into one bigger line of d squared, right? So if you want to compute the norm of a PEPS, what we need to do is to contract this square lattice network of these, what are also called reduced tensors. Okay, so let's try to do this. So here, for a bit of larger system, and the way we usually do this is to do this by a pairwise multiplication of tensors. So we can, for example, start up here, multiply these two tensors together, and then continue in some way. And then you quickly realize that the object we form here has as many legs as the linear system size, meaning that it's an object which scales exponentially with the linear system size, so the size itself and also the computational cost, right? So this sounds like bad news first, that we have an efficient ansatz, but if you want to compute something exactly, then there's an exponential scaling involved. But now the good news is that there exist several controlled approximate contraction schemes with which you can do this contraction in an approximate and controlled way. Now there exist different families of approaches. So there's approaches based on a NPS NPO formalism. So you make use of ideas and algorithms from 1D to contract the 2D PEPS. There's a family of methods based on the so-called corner transfer matrix method, which I will go a bit more in detail in a minute. And another family is called TRG, or tensor normalization group, which is typically used for a system with periodic boundary conditions. There exist even more sophisticated schemes like this TNR, or tensor network normalization, where essentially you make use of ideas of the MIRA, so with disentanglers for the contraction of the 2D network, but I will not go into the details here. Now, what all these schemes have in common is that the accuracy of this approximate contraction is controlled by another bond dimension, which we usually call chi. And then whenever you compute something, convergence in this additional bond dimension chi needs to be carefully checked. And then the computational cost of these algorithms is roughly between d to the power of 10 and d to the power of 14. So depending on the scheme, with a chi which scales roughly as d squared. Okay, so we have an approach which is not exponential without an exponential scaling, but it's polynomial with a rather high power in d. Okay, so let me now go a bit more into the details of the corner transfer matrix method, which is the approach people often use with iPEPS. And the idea is to, so we want to have an approach to contract an infinite 2D network. And imagine now that we want to compute some local expectation value here in the middle of the system. We can use now this CTM approach to compute what is called the environment surrounding this tensor in the middle here. And this environment is given by 4 corner tensors, so C1, C2, C3, and C4, and 4 edge tensors, T1 to T4, right? So this corner C1 in the end effectively represents in this infinite left upper corner of the system. The edge tensor T1 represents the half infinite column shown here. C2 represents this corner here, and so on. And the accuracy of this effective environment can be controlled by this boundary bond dimension chi here. Now, the CTM approach is a method to iteratively build up these environment tensors by letting the system grow in all directions in an iterative way. Now, let me show you here how you can let the system grow on the left side. So that's kind of called a left move. So what we do initially is that we start from some initial guess for the boundary, some initial boundary tensors C1 to C4 and T1 to T4. And then to let the system grow, we introduce a new column of tensors, so just a copy of T1, A, and T3, which we then absorb onto the left side of our system, right? So we multiply to the left. This will give us a new corner C1 tilde, T4 tilde, and C4 tilde. But these have an enlarged bond dimension in between them. So the last step we need to do is a renormalization step where we truncate this enlarged bond dimension to the bond dimension chi again. And now you see we have new corners C1 tilde, T4 tilde, C4 tilde, which contain an additional column of the system absorbed on the left. Okay, so this is called a left move. And then in a very similar way, we can also do a right move, and then a top move, and then a bottom move. And then we can reiterate this procedure over and over again until we have reached convergence. So for example, until a local expectation value here does not change anymore as we do more CTN steps. And this typically happens when the effective system size that we create here is much larger than the correlation length in the system. Then essentially what you measure here is the value then directly in the thermodynamic limit. Okay. So now the question is then, how can we do this normalization step And there's not a unique way to do this. So I don't want to go into the details here. Here for completeness, I just have one prescription which works well in practice. So which allows you to compute these projectors here, which can be used then to do this renormalization step here, for example, in the left move. Okay, so I will not go through the details. If anyone is interested, I'm of course happy to discuss this more. And now here I show you an example of the convergence here for the 2D Heisenberg model. So here's the energy per site as a function of 1 over this chi dimension for different bond dimensions, right? And then you see as we increase chi large enough, then the energy converges in chi, right? And especially if you look at the variations as a function of chi compared to the variations in D, you see there's a big difference, right? So typically what we do is to make sure things are converged in chi, and then we study properties as a function of D in the end, right? So we try to kind of remove the dependence on chi so that we can then just, we are left with a systematic study in D in the end. Okay, so this is the basic idea of the CTM approach. So this is what I wanted to just briefly tell you about the contraction approach, and we will see later that this CTM approach we also then use for other type of extensions then in the second part of my talk. But do you have questions up to here maybe?
Yeah, sorry, I didn't quite catch. So you said you make an Ansatz for the environments. So don't you already have tensors in the environments, or do you really start with a random guess?
So this is a random guess. It can be a random initial guess for the environment. I mean, what you can do in practice is indeed just take your bulk tensors that you have, and then project the boundary of this bulk tensor to something, and then use this as an initial boundary, right? So you can start from something which is random, let's say. So it should have the right symmetries, that you have a ket layer times a bra layer, so it should not violate the symmetry. But in the end, as you do, when you do sufficiently many CTM steps, in the end, what you measure here will not feel anything anymore what you had from the boundary you started from. I mean, let's say on the normal, in the usual case.
Okay.
Okay, but you're right that in principle. So I mean, what you also do in practice is to essentially initialize the boundary in some way from the bulk tensors that we have.
Okay.
That's a good question. Yeah.
Thanks.
Philip, I have a question. Could you comment on the relative pros and cons, if any, of the different methods to contract the PEPS? Like which one works best in practice, and is there any difference in like how do you decide? Like, I mean,
yeah,
does it depend on the state by which method works? I mean,
no, so,
are there any insights relating to yes?
So let me put it like this. So TRG is for periodic systems, and generally it's more difficult to contract a periodic system accurately. So in the end, if you look at an infinite system and you have open boundaries, then involved algorithms are typically really more efficient, and it's more easy to contract this. So in practice, doing iPEPS, it definitely makes sense to use an open boundary scheme compared to TRG, for example. Then MPS, MPO-based approaches versus CTM, I think in the end, I think they're in the end comparable, right? So then it's more or less a matter of taste what you would like to use. And also here, right? So you see this is really an active field of research. So people also come up with new ideas of doing this contraction, right? So here I showed you a CTM approach, which works in an iterative way. So we do step by step, but in principle, you can also directly try to solve things for the fixed point, which then can speed things up in case if the correlation length is very, very large. And similar ideas also exist here on these MPS, MPO-based approaches. So in the end, it's a bit system dependent, or what you're looking at, which approach could be favorable to the other one. But I mean, in the end, you can say that this is there's really a lot of different methods around. Many people try to reduce also the overall scaling here. For example, what you can do is to split Brown ket layers and then absorb them one after the other, which formally reduces the scaling of the contraction. But with the trade-off that you might need a larger chi to get a similar accuracy as in the conventional approaches. So indeed, there's many pros and cons. But let me say that at least in practice, we have been sticking a lot to just this conventional coordinate transfer matrix method, which often works in practice very well.
Okay, thanks.
Mm-hmm. Any other question? Okay, so if not, I would also like to go a bit, tell you a bit about the optimization. So the first family of optimization methods is based on the imaginary time evolution. So the basic idea is that if you apply exponential of minus beta h to some initial state and take beta to infinity, that this will project your initial state onto the ground state, right? And this is a complicated object, but we can approximate this using Trotter-Suzuki decomposition. So you can write this here as a sum over, so here we consider just the nearest neighbor terms, and then you can introduce a small time step tau equals to beta divided by n. So we split this into n small time steps, and if tau is small, that you can approximate the exponential of the sum by a product of these exponentials, right? So what this boils down is that you have these two-side imaginary time evolution gates that you want to multiply to your tensor network Ansatz between all nearest neighbor pairs. So let me just show it here for one dimension first. So here we have an MPS, and then this would correspond to one time step where we multiply these two-body gates between each nearest neighbor pair. And then we do this as many times until we have reached convergence. Now at each individual step here, we multiply such a gate to our MPS tensors. So we can multiply things together. And then of course, the result we would like to represent again as a matrix product state. So we can split this big tensor by doing a single value decomposition. And now typically this gate here will increase the bond dimension between these two tensors. So in the end, we need a truncation step, which here can be just done by keeping the d largest singular values. Okay, so that's the well-known TBD algorithm, some time evolving block decimation algorithm. And what's important here is that the MPS needs to be in canonical form with respect to the bond that you cut here. So it means that on the left here, you have unitaries, on the right here, you have unitaries, such that the SVD you're doing here in the end corresponds to a Schmidt decomposition of your wave function. And then it's known that if you keep the d largest single values, that this is gives you the optimal truncation. Right, so that's the basic idea here in one dimension. And now in two dimension, we would like to do a similar thing. So we have these time evolution gates we would like to apply between each nearest neighbor pair. This will increase the bond dimension between two tensors, and then we want to truncate this back again to the original bond dimension. Now the problem is that the standard SVD type update, like in TVD, is no longer optimal. And this has to do with the fact that when you consider a bond here and cut it, you no longer split your wave function into two pieces, right? So it's no longer a bipartition, because the wave function, the left and the right side of the wave function is also connected by the other bonds, right? So because of these loops in the ansatz, you don't consider a bipartition, or in other words, there's no canonical form in the PEPS, right? Now you can still do this. So you can still use this TBD-like truncation. So it's not optimal, but it still works reasonably well. And the advantage of this approach is that it's computationally very cheap, right? Because it's really just acts in a local way, and you can just forget about the rest of your wave function. So it's a simple approach. That's also why it's usually called a simple update. But it's not optimal. So if you really want to do an optimal truncation, what you need to do in 2D is really include the entire 2D wave function in your optimization, which means that for each optimization step, you need to contract your 2D tensor network, which is computationally much more expensive. And there's tricks how to make this as efficient as possible. So it's called a fast full update, where you recycle as much as possible from the previous steps. So you recycle the previous environments that you computed from the previous steps. Okay, so here I show you a comparison of the two approaches for the 2D Heisenberg model. So that's for the order parameter. Here you see the, the quantum Monte Carlo result. Here's the quantum Monte Carlo result. So here you see the simple update, which, it gives you the correct state, but an order parameter which is too high. And then at some point it flattens out and converges to a value which is too high, right? And then here you see results from the full update. You see the order parameter goes down and approaches here the quantum Monte Carlo result. Okay, so in the end, you see there's pros and cons for both approaches. So this approach, with this, you can very quickly scan over an entire phase diagram and get some first results within a few minutes. And then you can always use the more optimal approach to refine things later on again. So, I mean, in the end, you can really see them as complementary. Okay, so this is now, this was imaginary time evolution, and let's now also discuss the other family of approaches based on energy minimization. So actually the energy minimization for finite PEPS was already developed many years ago. And in the end, this works very similar as the one-side optimization for matrix product states, if you know that one. So the idea is that you try to optimize the energy with respect to one tensor while keeping all the other tensors fixed and then sweeping through your lattice, right? So you select the tensor A, you optimize the tensor A by minimizing the energy. And if you do that, one can show that this boils down in solving a generalized eigenvalue problem. So where X here is the tensor A reshaped to a vector, N is the tensor network representing the norm around this tensor A, and this is the tensor network representing the Hamiltonian. So for simplicity, I just show it here for one dimension, what this corresponds to. So H is this tensor network here, so Brand-Ket, which with the Hamiltonian sandwiched in between, and this is the norm environment of this tensor A. Okay, so you can solve this generalized eigenvalue problem. This will give you a new tensor A that you can plug back in your PEPS Ansatz, and then you can move on. You can then take the next tensor, optimize for this one, while leaving the other tensors fixed. Okay, you can just repeat this until reaching convergence. Okay, so this is for finite PEPS. Now, if you want to do something similar for infinite PEPS, there's some additional challenges. So first, since we're considering an infinite system, you need to take into account infinitely many Hamiltonian contributions, right? So here you have an infinite number of Hamiltonian terms that you need to take into account. Now, there's different schemes to do this resummation. I will briefly mention, show you how this works based on the corner transform matrix method, but there's other schemes based on so-called channel environments, which was developed in Frank's group. Or in the end, you could also use a PEPO approach, so encode the Hamiltonian in a PEPO, so the 2D version of an MPO. And then the second challenge is that the tensor A here now appears infinitely many times in your iPEPS, not only a single time, meaning that solving the generalized eigenvalue problem will not give you the optimal solution, right? And there's also ways to take this into account. So some time ago, I considered an approach where I take an adaptive linear combination between the old and the new tensors, so doing a line search in this mixture here, or more straightforward is to just compute the gradient, so the energy gradient, and feed the gradient to a conjugate gradient approach. Okay, so now let me mention now how you can do this Hamiltonian summation, or at least one way how to do it, right? So we already know how to represent the n part here, right? So this, we can just use the corner transfer matrix to compute this environment, which in the end corresponds to this n part. But how about the h part, right? So this really contains all the infinitely many Hamiltonian terms, and we can now also do this in the framework of the CTM by introducing new types of environment tensors, right? So here I introduce a new environment tensor C1, which includes all the Hamiltonian terms sandwiched between Brand-Ket layers summed up, right? So this represents this sum here. So this contains all the contributions in the upper left corner, but of course there's more contributions. The Hamiltonian terms might also live in this corner here, or in the edge here, or then terms connecting an edge with the corner, and so on. So in the end, what you see here are all possible contributions where your Hamiltonian terms can live. So if we sum up all these, then we have a representation of this expectation value where H is an infinite sum of Hamiltonian terms. And now the thing is, we can also use the CTM approach now to compute these environment tensors in an iterative way. So similar to the left move I mentioned before for the norm, we can also now do a left move for the energy environments where we just resum things in a systematic way. So I will not go into the details here because in the end, this is just a matter of bookkeeping. So you want to just add up all these different energy contributions such that in the end, they're contained in these energy environment terms. Okay, so here I show you the results now for this approach. So that's again for the 2D Heisenberg model. Here you see the relative error in the energy with respect to the extrapolated quantum Monte Carlo result. And then you see here's the variational update, so the energy minimization, and you see we can even get a higher precision than with the full update imaginary time evolution algorithm here. And for the largest bond dimension here, you see we're actually already very close to the extrapolated quantum Monte Carlo result, even without doing any extrapolation, right? So this is extremely close to the true ground state. Okay, so I've given you a very brief overview of different optimization methods. So that's not the end of the story. So people are still further developing these approaches. And in the end, this is also really the biggest bottleneck in the simulation, how to do this optimization in the optimal way. And I think one of the a very exciting recent development, which I would like to mention, came out last year, namely the idea of computing these energy gradients not by writing out many diagrams, but actually letting this be computed in an automized fashion. So here in this paper, here they describe how we can use ideas from machine learning, so-called automatic differentiation, which allows you to compute these gradients in an automatized fashion. And the idea is that all you need to feed in the end is just a function which computes you the energy. And then based on that function, the library itself can then do a backpropagation and recover the gradient with respect to the elements in the tensors. So I will not go into the details here. We're currently also checking this out in more detail in our group. But I think it's a very promising direction, and I believe it will also have a nice impact on tensor network calculations, because in the end, it really simplifies the coding quite a bit. Okay, so with this, I have completed kind of the brief or overview introduction of PEPS. And do you have questions up to here?
I have some questions.
Mm-hmm.
You mentioned the simple update and that this is much faster because you don't have to contract the whole network. But how do you get the energy, or how do you calculate any expectation value in the end? Do you have to contract it in the end, or is there smarter ways of doing this?
Exactly. So that's actually yes. So you do the optimization without any environment, but then in the end, if you want to compute the expectation values, then at this stage, you then need to contract things. So then at this stage, you then need the contraction. But of course, there's a huge difference if you do, you know, thousands of imaginary time evolution steps, and each step you have to do CTM steps. This is way more expensive than just doing it at the very end of the simulation. But it's a good question, yes.
Okay. And I have another question. You talked about this variational optimization for iPEPS. Do you know if it's also applied to finite PEPS?
Yes, so this in the end, the finite PEPS is really the thing which was already out a long time ago, right? So this is sorry, this is, let me see here. Yes, so that's already back in 2008. That was already used back then.
And people really used it, because I just saw this paper as well, and it mentions the idea, but I didn't see any numerical results of this.
Yeah, so there are some examples. Let me think. More recently, I'm not entirely sure what's the latest thing.
Okay.
Finite PEPS. Yeah.
Maybe Mari Carmen with Lubash, no? Did a lot, all the PhD study of
There's a benchmark paper exactly there. Yes, I remember that one. But after that, yes, I'm not sure application-wise if there was anything out there.
And how about the TRG-related methods to contract the network? This is used a lot for the path integral formalism, but is it also used to calculate the environment for this Hamiltonian-based approach? Do you know if people implemented that?
So some people still do calculations based on TRG. I mean, of course, if you're interested in getting quantities for finite systems with periodic boundary conditions, then that's the method of choice, or the more sophisticated versions like TNR. If you really look at the infinite system, then I don't see much advantage of using TRG over just conventional CTM, because the computational cost in CTM is in the end lower than in TRG.
Okay, thank you.
Thanks. Okay, so if there are no more questions, then I would like to come to the more recent developments. And the first thing I would like to tell you about is recent progress in doing finite temperature simulations with iPEPS. So there has been quite some methodological developments over the past 10 years. And we also had some recent work here together with Piotr Czarnik and Jacek Jarmaga, who have already been working on this topic for quite some time. Now, the basic idea is simple, right? So we know how to use a tensor network to represent a wave function. But now we can also use a tensor network to represent an operator, like a thermal density operator, right? And now instead of having just one physical leg, for an operator, then on each side you have an incoming physical leg and an outgoing physical leg, right? And you can use this as an ansatz to represent an operator in 2D. Now there exist approaches which use this as an ansatz directly for a thermal density operator, so just a single layer of this, which has the disadvantage that you might lose the symmetry properties of the density operator, right? So which should be Hermitian. So due to truncation effects, it could be that this is no longer Hermitian anymore. So what we did more recently in our work, I mean, it's just instead of having one layer, we use 2 layers. So we use this ansatz here to represent the density of the thermal density operator at half the target inverse temperature beta. And then we combine it with its complex conjugate to get the thermal density operator at beta. And this is then Hermitian by construction, right? So this has the right symmetries. And the other advantage is that we have a double layer scheme, very similarly to what we do in ground state calculations, such that actually we can start from our ground state approach and just do some small changes in the code to use the same algorithms then also for density operators. Now, how can we get a representation at a certain target beta here? This can be done again just using an imaginary time evolution. So I already explained you the main idea for ground state simulations, and the same thing can now be used also for finite temperature simulations. Now the starting point is exact, right? So if you take beta equals to 0, then the thermal density operator is just an identity. So we can represent initial state simply by a product of identities. So here just in one dimension, product of lines. And then we want to time evolve this in imaginary time down to our target beta here. And again, as discussed before, we can do this using a Trotter-Suzuki decomposition, right? So we have the same thing as before here, just that we have here an additional leg sticking out. So this is in 1D, and in 2D, it's the same thing as we discussed before. So meaning that at every time you apply a gate here, there's a truncation involved. And in 2D, it means then that you can either use the simple update or the full update to truncate the bond after each application of a gate. Okay, so imagine now if you want to compute the trace of this row, then in the end we connect, the blue and the green lines here, And in the end, another way to look at this is simply if we join the green and blue lines into one line, then you see what we obtain here has the same structure as for wave functions, right? Just two layers. So it means that starting from here, you can then really use exactly the same CTM algorithm as we used for wave functions to contract the network representing the thermal density operator. So you can really recycle a lot from previous codes. Let me also mention here that we can look here at the things in a different way. So we can also see this as an ansatz for a purification of the thermal state, right? So where the green ones are the physical sites and the blue legs are ancillar sites, and where we recover the thermal density operator simply by taking the trace over the ancillar sites of Ket and Bra here, right? So in this context here, it's really the two approaches are equivalent. Okay, so the message in the end is that using this scheme, in the end, you can just build upon previous ground state algorithms, change a few lines of codes, and then you have an approach that you can also use to obtain properties at finite temperature. Now, let me show you here some recent results based on this approach. So we recently applied this method to the Shastri-Sutherland model. So that's an effective model of this material, strontium copper borate. And essentially, it's a 2D Heisenberg model living on this lattice. So besides square lattice interactions, we have here these additional interactions on these diagonals. Now here I show you results for the specific heat for different ratios of these two different interactions. Now if we go to a coupling ratio of 0.5, then there is a sign problem in quantum Monte Carlo, but it's relatively weak. So we can actually do a comparison with quantum Monte Carlo here. And you see we have a very nice agreement down to low temperatures. But now, as we start increasing this coupling ratio, so as we approach the value which is relevant for the material, then quantum Monte Carlo has a strong sign problem, which means, as you can see here, the error bars explode as we go to low temperatures. So they become exponentially large as we go to low T. So it can't access the low temperature properties anymore. But with iPEPS, you see we can still obtain here the low T peak in a controlled way. And then in the end here, I show you a comparison between iPEPS and the actual experimental data, where you can see we obtain a nice agreement at low temperatures. Now at high temperatures, things start to deviate here, but this is because the model is no longer accurate, because spin-phonon coupling terms become relevant here, which are not included in this basic spin model here. Okay, so in the end, it looks promising that we can use iPEPS not only for ground states, but really also to address challenging problems at finite temperature, which are out of reach by quantum Monte Carlo due to the negative sign problem. Okay, and then the next thing I would like to mention are computations of excitations with iPEPS. So the idea here is to start from a ground state representation of the wave function and then build an ansatz for the excitations as follows. So we take the ground state iPEPS and then we modify one of the ground state tensors into a new tensor. So replace here these tensors with a new tensor B here at position X. And then we take a momentum superposition of this ansatz. So this sum here, and this will then be a state with correspond to a state with a well-defined momentum. Okay, so this is an approach which has been worked out in detail first for matrix product states. So in the group of Frank Verstraete, so especially Yuto Hegemann was involved here. And then later this idea was then also extended to 2 dimensions for iPEPS, and especially worked out by Lawrence van der Straten. Now, what is the challenge here? So the challenge here is that the ansatz itself is not just a single tensor network, but a sum over tensor networks, which then means that this object here is actually a triple infinite sum, right? So you have an infinite sum here, you have infinitely many Hamiltonian terms, and another infinite sum here that you need to evaluate or when you want to minimize with respect to the new tensor elements. Now, if you exploit translation invariance, you can bring it down from a triple sum into a double infinite sum. But still, this seems in 2D very difficult to do. And I thought for quite some time that this would not be possible. And then Lawrence and co-workers came up with an approach based on these so-called channel environments. So I will not go into the details. And more recently, we also realized that we can actually also use just the plain CTM approach to do this double infinite summation. So this has been worked out by my student Boris Ponsiun, who, yeah, so he really implemented this all in full detail. And now the idea is very similar to what we have seen in the variational optimization based on the CTM, namely that we need to introduce new type of environment tensors to represent this expectation value. So we have now environment tensors for the norm. So as in the standard CTM, we have environment tensors containing the sum over all energy contributions. So that's these ones here, so which we saw already in the variational optimization. Then you have environment tensors containing the sum over all these P tensors together with the correct phase factors. And then you also have the environment tensors containing both. Okay, so you can just list all the contributions which are relevant here. And then again, you can then get these environments in a systematic way in your CTM steps by just adding up things in a consistent way. Okay, so again, I will not go through the details, but let me say it's just a matter of bookkeeping that you don't forget any term here. And then in the end, after the CTM procedure, you then have all the required environments to represent this expectation value and to feed this then in some minimization algorithm to get your parameters for the B tensors. So here are some benchmark results again for the 2D Heisenberg model. So for the lowest lying excitation, so the dispersion. We also compared this to quantum Monte Carlo, where we got a good agreement. And then let me highlight here, so here at momentum 0, 0 and pi pi, so it's a gapless system. So here we should obtain something which with a zero gap here. And you see at finite bond dimension, we always obtain a finite gap, but it systematically becomes smaller as we increase the bond dimension. And if we extrapolate here, we actually obtain something which is consistent with a vanishing gap here. Okay, so these are some initial results. But in the end, I think it looks promising that we can really also use iPEPS as a tool, not only for ground state, but to study also the nature of the low-lying excitations. Okay, and then in the very end, very briefly would like to mention this approach called finite correlation length scaling, so just in one slide, which in the end is an approach for the systematic study of continuous quantum phase transition. And the idea here is very similar as in standard finite size scaling analysis, just with the difference that instead of doing the scaling analysis in terms of different system sizes, we do it in terms of an effective correlation length that we extract from our tensor network, right? So if you take a system at criticality, then the finite bond dimension will induce a finite correlation length. So the larger D, the longer the correlation length, but it will never go to infinity, at least in 1D. It will never go to infinity, but always be finite. And then you can use this as a parameter to do a finite size scaling analysis. Now this has been worked out in detail already a long time ago for matrix product states. And more recently, we also extended this and tested this in 2 dimensions with iPEPS. So that was worked together with Piotr Czarnik, Geert Kapteins, and also Luca Tagliacozzo. And then at the same time, there was a paper also by Michael Rader and Andreas Leutli, who had the similar ideas and also complementary results. Okay, so in the end, this approach allows you to extract critical couplings and critical exponents in a systematic way. Here I just show you an example of a data collapse plot. So if you know this from a standard finite size scaling analysis, so here all the data collapses for each value of the bond dimension, from which we can then extract here the critical exponents and the critical coupling. And we can use this approach also as a tool to extrapolate order parameters in gapless systems. So here I show you data for the 2D Heisenberg model, so for the staggered magnetization squared, where we plot here the data now as a function of 1 over this effective correlation length. And you can see here that we can extrapolate this data quite nicely here to the infinite D limit, where we obtain a nice agreement with quantum Monte Carlo. Okay, so this was only very brief, but in the end, I think it's a promising tool in the end for the study of critical phenomena in 2 dimensions based on iPEPS. Okay, so with this, I'm at the end. Let me just briefly summarize. So I guess everyone agrees that 1D tensor networks have been a state-of-the-art tool for several decades already. Two-dimensional tensor networks are somewhat more challenging, but there has been very nice progress in recent years. And especially iPEPS, I think, has become a powerful and competitive tool really to study challenging problems. So in condensed matter physics, there are already many applications, but I really believe this is also going to be a powerful tool for applications in high energy physics. There has been a lot of development also for algorithms beyond ground state calculations, but it's not the end of the story. So there's really still big room for improvement to get higher accuracy, to push things to larger bond dimensions, new types of extensions, and new types of applications. Okay, so with this, I would like to acknowledge my collaborators, especially the ones here now involved in these recent developments, and people from my group, and I would like to thank you for your attention.
Okay, thanks, Philippe. Thanks for this very nice and clear talk. Are there any questions? Okay, seems not. Seems like it was a very clear talk.
Sorry, Philippe. I have a question. I mean, I'm not sure if this mechanism of raising hand works. So, in the context of what you were discussing, like how interesting is to look for time-dependent phenomena?
So, by time-dependent phenomena, you mean a real-time evolution?
Yeah, of course.
Yes. So, well, I mean, the situation is similar as in one dimension, right? You can do it up to a certain time scale, but the problem in the end is that the entanglement can grow quite rapidly. So you will be limited in the end by the time scale that you can reach. But depending on the problem, in the end, you can you can try, let's say, right? So I mean, on the formal level, the algorithms are you can just use. Well, there's different time evolution algorithms that you can use in this context, but in the end, it's not so much a matter of the algorithm, but more in the end, a matter of the entanglement growth, right? So that's one of the challenges. But it might indeed then depend on the problem, what you're interested in, how far you can actually go. But I have not tried much myself, let's say, in this direction.
Okay, thanks.
Thanks.
Okay, any last questions? Okay, if not, I would just like to thank Philippe from everyone, of course. Thanks, Philippe, again, for this nice talk.